Okay, thank you very much. Firstly, one order of business from yesterday, I was epsilon away from the correct statement of Mcmullen's theorem. So just for those who are still paying attention, here's the correct statement. I was actually a parentheses away. For all tangled subsets V in the space of polynomials, for any collection of polynomials that's tangled, that you can have one of these pseudo-null braids, there's an open subset of that set of polynomials cross choices as some of initial guesses so that your iterated algorithm will fail. As people were pointing out, like, dude, any algorithm will succeed if you happen to pick the root itself. You will find it. And so it's because it was open in the product. Thank you, people, yeah. Okay, but I decided to do something a little radical with my talks. I am not going to talk about representation stability per se, like the definitions, and we've been getting all these great talks on rep stability and FI modules. But I thought I'm going to, here's a question that you could ask if you were a graduate student, although I think it was already sort of answered in the talks, but like, why do you care about the cohomology of these different spaces? Why do you care about cohomology of the space of polynomials as a representation? Great, the representations stabilize. That's cool. It allows you to compute them. It takes an infinite problem and makes it a finite problem, namely the infinite problem of understanding the cohomology of like the space of degree n polynomials for all n, and it makes it just a finite problem. You only need to do finitely many. But why do you care about those representations in the first place? And there's tons of meaning. My answer to you is those representations have geometric meaning, arithmetic meaning. They're encoding a huge amount of deep and subtle information and incredibly concrete information. And what I want to do in the lecture today is to go all the way down to very elementary topics, but to explain how this fits into a bigger picture. I wanted to give the arithmetic meaning of those representations. And I want to start with one of the sort of most amazing achievements of mathematics, due to me. No, I'm just kidding. No, it's really due to Andy. No, it's this amazing bridge. It was great because like Ravi yesterday was like, yep, this is one of the greatest achievements in mathematics, definitely. You could definitely talk about human thought. It's just amazing. It's the whole series of ideas surrounding the Weil conjectures, this kind of bridge between arithmetic and algebraic geometry on the one side and topology on the other side, where on the one side you take an algebraic variety and you look at its complex points. That's a nice manifold. And most of the people at this conference, we can study this because we can study manifolds. On the other hand, you have finite sets. You want to count solutions to equations, let's say over fq or fq to the d. Q is a prime number. And that's just some finite set with no structure. And there's a bridge between these two things. That's like level one. And I'm going to develop a little bit of what I think are sort of maybe possibly new entries in the bridge, new reflections. One, homological stability here. This is sort of goes back 7 years or something to like Venkatesh, Ellenberg, and Westerlund. Like homological stability here, some kind of stability here, and then representation stability definitely fits in. It's like a new plank on this bridge. So let me tell you what I'm talking about. Let's go, and let me first do a little tiny review before I do. I was going to do this whole big impressive table, but it's now only, yeah. So let me just talk about polynomials over finite fields. I'm going to stick with our working example of polynomials, but there's lots of other algebraic varieties in the world. And I would say right now is a very exciting time in the theory because it's clear there's applications and people are starting to work out some of them. But for like any algebraic variety you want, you start, there are lots of other examples, and I'll mention them. But let's talk about polynomials over fq. Q is going to be fixed forever, and it's a prime, or a power of a prime. And I'll just remind you that, when you take a polynomial, just a quick reminder since it's a topology conference, you take your favorite polynomial and you want to understand the zeros, say, where do the roots lie? And you think of this as a polynomial in fq of t. Yeah, the first thing we see is that fq of x. Okay, polynomial ring over fq. Right? Whenever you have a polynomial where the entries happen to be the coefficients are integers, you can always just reduce mod q. So where do the roots lie? And this depends on q, and it's already pretty deep. Even this polynomial. Well, if you look over f3, what do you get? You can be 0 or 1 or 2, mod 3. If you plug in 0 or 1 or 2, like 2 you get 5, which mod 3 is 2. So there's no zeros, no roots. And of course, what's happening is, just to remind you, there's this tower. You have f3, then f3 squared, then f3 cubed of finite fields. And if you have here, the roots, say the roots are plus or minus, say that no roots in fq, in f3, but it does have roots in f3 squared. Let's say they're epsilon and minus epsilon are the roots. They are literally, this is how you can define f3 squared. It's the roots of this equation. Epsilon and minus epsilon are sitting in here. And in fact, as you know, f3 squared is a vector space. Over f3, it is spanned by 1 and epsilon. Right? It's a two-dimensional vector space over f3, spanned by 1 and epsilon, where epsilon's a root of any quadratic equation. So you're just formally adjoining them. And in general, when you have a degree d polynomial, it's in all the roots are in f3 to the d, but they can lie in different levels. And it depends on if you look in f5, p has roots. Let's see, you plug in 1, no, 2 has roots. 2, you plug, right? 2 squared plus 1 is 5, which is 0, mod 5. And then the other root should be minus 2, which is the same thing as 4, or 3. No one said I could add. Yeah, has roots 2 and minus 2 in fq, in f5. So it definitely depends. And in fact, quadratic reciprocity says that p of x equals x squared plus 1 has roots, has a root in fq if and only if, this is like the baby version of quadratic reciprocity, if and only if q is congruent to 1 mod 4. Okay, so there's an interesting discussion, even for the polynomial x squared. Q is always prime. Like I said, Q is always prime. Oh, sorry. I said power over prime. Q prime. OK, so any questions? Another way to say, let me just say, another way to say root, so a root lying in FQ is the same thing as saying a linear factor when you factorize over FQ. And a root in FQ squared is saying an irreducible quadratic factor. A root in FQ squared that's not an FQ, quadratic or linear factor. And a root in F Q to the D is the same as irreducible degree D factor. So there are two ways of saying the same thing. So this polynomial does not factor over F3. It's irreducible over F3. And over F5, it must be x plus 2 times x minus 2. Let's see. Yes, x squared minus 4, which is x squared plus 1 over F5, yeah. Okay, any questions? So if you want to tell me the roots and where they lie, it's the same thing as factoring over FQ. Just like with real numbers and complex numbers, it's this analogy. So questions? Okay, so I want to look at all the polynomials. So what we're going to look at is, sorry, I'm getting some of these things. Okay, I now want to look at the poly sub n, I'm going to call it poly sub n of FQ equals the set of monic, square free, degree n polys over all polynomials over FQ. And here's the case Q equals 3 and n equals 3. So that's this definition, and here's the case Q equals 3, n equals 3. So there are 18 of these. There's t cubed. You just start going, and you're like, OK, what does it mean to be square free? What are the roots of this? You want to make sure there's no repeated roots. And we can all see that, like, let's see, 0 is a root. 1 is a root. You just have to show no repeated roots, right? And we all know there's like formulas for telling you when there's no repeated roots. There's the derivative test. So you can list all 18 of them out. Sorry, this would be a little more impressive if I could list them all out, but I won't. And now, what do I want to do with these? So it's really interesting. You can say, firstly, how many are there? There's 18 of these. Right? Well, not right. I'm telling you there are 18 of them. But how many polynomials are there, monic polynomials over F3 are there? Total number of monic polynomials. Right. So it's not that hard to count how many square free polynomials you have. It's not totally trivial. You need a little bit of an argument. But let's see. If you give me a cubic polynomial, t cubed plus a1 t squared plus a2 t plus a3, well, there's q choices for a1, a2, and a3. So there's q cubed polynomials. So 3 cubed is 27. So there's 27 polynomials. 18 of them are square free. And one interesting thing, if you look at the number, so here's a question. Firstly, let me just give it a few questions. Some questions, some very basic questions. This is sort of an introduction to what's called maybe the newly burgeoning field of arithmetic statistics, which has maybe been going on for a decade, although in some ways for a long time. But some basic questions. What is the probability? So question 1 would be, what is the probability that a random monic is always just for simplicity, monic degree d polynomial over a finite field, what is the probability that a random degree polynomial in this is square free, has no repeated roots, has no root of multiplicity 2? So for d equals 3 and q equals 3, it's 18 out of 27. You just take the total number of square free guys and divide. So that's the first level question you can ask. And we are going to give the hardest known proof of that first fact. But it's going to reveal, I think, a lot. And this will be, for people who have heard, this is the Grothendieck-Lefschetz fixed-point theorem. All other questions I'm going to give are going to come from representation stability, is the punchline. I can never help giving out the punchlines to my jokes. What is, so now what this allows us to do is to reduce a lot of questions about arbitrary polynomials to square-free ones. Because everything I'm saying about square-free, you can then convert it to polynomials. But let me just look at square-free. What is the probability? What is the, maybe I'll say it this way, expected number of linear factors i.e. roots lying in FQ of a random polynomial, I'll call it P in poly D of FQ. This is a quick way of saying monic square-free polynomials of degree D. So you can just compute this. You list out, and we do this in our paper. Sorry, this is all joint work. Youch. What a horrible guy. Joint work with Tom Church and Jordan Ellenberg. Oh, I can't believe you're taping this. Will you please snip that and put it in the beginning? Yes. Yeah, and in fact, I learned all this stuff from these guys, so it's even worse. And so what we do in our paper, we have a few papers, but one of them is called representation. It's called counting. Counting is in the title. It's counting points of varieties over finite fields. Representation, stable cohomology, and counting points. ... counting ... So we list out the 18 polynomials. Degree 3. The 18 elements of poly 3. These are the elements of poly 3 of F3. There's 18 elements. And what's cool is you then look and you say, OK, I'm going to frickin' find all the roots of all the polynomials. So this guy, and I'm now going to list how many linear factors. This guy has 3 linear factors. There's a whole huge group of guys. You can't have 2 linear. You can't have, 2 linear, just 2 linear factors. Because if I have 1 linear factor, I factor it out and I get a quadratic. And he's either irreducible or not. If he's irreducible, I have no more linear factors. If he's not, I get 2 more. Because remember, the things are distinct. So these guys all have 1, and these guys happen to have no factors lying in FQ. And so let me just write down the computation. What do I want to do? Sorry, this is ridiculous. For some reason, I didn't write this. So the expected number of linear factors, so let me do it for poly 3 of F3. How do you compute the expected, if I give you a polynomial, the expected number of linear factors? I add up the total number of linear factors of all polynomials and divide by the total number of polynomials. So in this case, we've got one guy who's got 3 roots lying in FQ. 0 guys that have 2 roots lying in FQ. 9 guys that have 1 root. You just count these. And 8 guys that have no roots in FQ, in F3. And what did I say? We have 18 of these polynomials altogether. So any questions on this? Now this is 12 over 18, which is 2/3. But I'm going to write this as 1 minus 1/3. Why am I doing that? Well, I want to try to find patterns. So the answer to the first question is elementary. And I will actually give the hardest known proof in the world, but then I'll give a better proof. That's an easy proof that you could give, that you could ask a freshman to do. But I'll be computing in the ring of motives. But you realize the freshmen are doing that. That's a hint for future talks. But anyway, there are 54 elements of, you look at square-free polynomials in F3. Degree 5. Let me just jump up to 5. Oh no, cortex. Let me go to 4 in F3. So the formula here, by the way, is the number of polynomials of degree n over fq that are square free. We will see soon that it's q to the n minus q to the n minus 1. So when you plug in q is 3 and n is 4, you get 3 to the 4th minus 3 cubed, and that's 54. So there's 54 elements, and you, here's how the computation works. You get, there are 0 with 3 linear factors, plus 2 times 9, plus 1 times 24. There are 24 with 1 linear factor, and there are 21 with no linear factors. I'm like literally just, you count, you ask a computer to do it. And this is 42 over 54, which is 7/9. But I'm going to, it's 1 minus a third plus a ninth. And I'll just jump up to the next one. There are 162 polynomials. Sorry, I really want to do this because I want to give you like some kind of feel for this. Hopefully it's, I'm trying to make the theorems come alive. And it's a very complicated, it's like 3 times 3 plus 2 times 4 plus 1 times 63 plus 0 times 72 over 162. And if you, it's funny, you write it 1 minus a third plus a ninth minus a 27th. So I think you can sort of see this pattern. You keep adding a term. This is a very simple problem. We're going to get to incredibly complicated problems. But if you understand this one, I think it really elucidates the general one. But I just want to do one more. This is in, I want to do the degree 5 polynomial. We just did degree 5 polynomials over F3. What happens when you do like F11? Just to pick another prime that's a little bigger. It's totally awesome. So in other words, I'm counting the expected. Remember, all of these things, expected number of roots lying in F11. Right? That's what we're counting. How many roots do you expect to lie in F11? Yeah, so here, just to step back for a second, you can see in all of these cases, you expect it's a little less than 1 root should lie in. That's not obvious at all. You have 3 of them. So it's a little less than a third that one of them lies in there. Right? But here you get this number. It's 134,200 over 1,400. Yeah, sorry, whatever this number is, 146,410. But when you write this, it ends up being, if you know how to write it the right way, and you'll notice there's a similarity of these formulas. Yes, 121. 11, 11 squared, 11 cubed. They're the same formula, of course. It's just the prime you're plugging in is different. So the fact is, the general fact is that the expected number of roots of a random element of a random polynomial monic degree d in FQ is exactly 1 minus 1 over q plus 1 over q squared minus 1 over q cubed, dot, 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 and it ends with, depending on the parity, q to the n minus 2. And in fact, this converges to like a formal power series as n goes to infinity. Okay, so we ask these questions. What's the expected number of linear factors? So we're thinking about this probabilistically, like what are the moments of this in the sense of probability? Oh, D, yes. D's and N's are always for me. I can never decide, so it's like 50-50 chance. Sorry. What are the moments of this kind of probability? What are the expected number of degree m factors? How many irreducible factors? There are lots of other kinds of statistics you could ask. What's the expected discriminant of the polynomial? Yeah, and we'll get into these. And it turns out this kind of stability, I would call this stability in the sense that this is converging to a kind of power series, right? So it depends on the n. It depends on the degree of the polynomial. There's all these different patterns going on. One of them is that it doesn't depend on q, on the prime. Here's the I just gave the formula. It sort of doesn't depend on q in the sense that this is for any q. But there's a stability going on in that it depends on the degree d, but in the limit, it just converges to a given answer. So in that sense, it's some kind of stability. Guess what? That is reflected in and reflects the fact that the cohomology of the space of polynomials over the complex numbers, the one we're talking about, has homological stability. And that's what I want to explain. And that's a totally amazing fact. And you can actually prove one from the other. You can literally do elementary calculations, and then that will imply homological stability, like due to Arnold. Of course, you have to apply this massive bridge. You have to walk across the bridge from arithmetic and topology. But I want to show you this bridge, and I hope to advertise to more topologists that you don't have to read all of EGA and SGA. You just have to know someone who has. No, but actually, it's better than that. You can really learn how to compute with this stuff and get answers. And you have to make sure everything is like legal, and you have your guru. But there's definitely a whole distinguished history of this. Actually, if you look at Deleen's interview in the Simon Center, they interviewed Deleen. And they said, boy, you never worked with anybody in general except like Lustig. He has a famous collaboration with Lustig, who's George Lustig, super famous representation theorist at MIT. And he said, how did that happen? And he said, Lustig came to me with all these amazing ideas and like computations that weren't like officially working, but using a tall cohomology. And but he didn't actually know Étale cohomology. He didn't know like the rules of the game exactly. He knew how to compute with it. And the ideas were so great, like I had to join up and like make it all officially work. So I'm not like likening us to Lustig. But yeah, anyway. But you really can, and we've been doing this. So anyway, and I hope to explain like how to you. And we'll see how representation stability fits in. Okay, so let's get to, great. So let's get to some more specific mathematics. I'm telling the story for polynomials, but in our paper we also consider statistics. You take a finite, we're telling new things about and giving new proofs of old results. You take like, this finite group. This is a finite group of Lie type, GLNFQ. There's something called like a maximal torus, maximal diagonalizable subgroup. How many are there? It's not so easy. That's a famous theorem of Steinberg. How many, how do you expect the eigenspaces to split up over FQ, FQ squared, etc.? All those things, there's an analogous story that we tell in our paper. So there's definitely tons of other examples. And we've just done the two of the simplest. So let me explain how this all works. What's going on? And this actually links to my other talks and to actually a lot of the talks that have been given. Okay. So please feel free to interrupt at any time if you have any questions. So, great. So, poly n. So, oh, I think I have it somewhere. Great. So again, poly n is the space of monic square-free polynomials. And the key thing is when you have a polynomial, so I've mentioned this before, if you look at poly 2, let's say over the complex numbers, the space of monic square-free polys, it's the set of x squared plus bx plus c, meaning it's really the set of pairs, bc, where b and c are complex numbers, and b squared minus 4c does not equal 0, right? That's the condition for a polynomial to not have repeated roots. For poly 3, it's the set of x cubed plus bx squared plus cx plus d. It's really triples of points, b, c, d. So b, c, and d. So by the way, already for quadratics, we see this is a very interesting algebraic variety. This algebraic variety is sitting inside c squared. It's a hypersurface in c squared. It's described, it's a complement of a hypersurface. The hypersurface described by the equation b squared minus 4c. Right? This is the set of pairs b comma c. And here, what is the condition for a polynomial to not have repeated roots? This is something we all learn in elementary school. It's b squared c squared minus 4c cubed minus 4b cubed d minus 27 d squared plus 18 bcd does not equal 0. Right? We all learned this in elementary school? Everybody? Right. So this, of course, it's called the discriminant. The discriminant, I'll say delta of a polynomial, it's like delta in this case of b, c, d. The discriminant is a polynomial. In general, this is very easy to prove, and this I think you do prove in algebra classes. The condition for a polynomial to have a repeated root is polynomial in the coefficients. So if I want to know if this polynomial has a repeated root, I don't need to find the roots and check if they're the same. And this works over any field, actually. All I need to do is you give me the polynomial, so you're giving me b, c, and d. I just plug in the numbers and see if I get 0 or not. And because of this, and this is true for all, but the polynomials get incredibly complicated. I think for degree 6, there's like 250 terms or something like that. This goes back 300 years. But this shows that, I'll just say the correct words. It's a poly sub d. It's a scheme defined over Z, but I'll just say this is an algebraic variety. This means you're described by polynomial equations in either projective or affine space. Algebraic variety defined over Z. Defined over Z means the coefficients defining the algebraic variety are integers. Here the coefficients are 1, minus 4, 27, minus 27, right? So you're defined over Z. Whenever you have such a thing, you can do two things. You can extend scalars, and you can consider the set of complex points of your variety. But you can also reduce mod q, and you can look at you can think of your equation as you can reduce everything mod q, and everything here makes sense. And you can look at the set of this set, the FQ points of this variety, and it represents all monic square-free polynomials over FQ of degree n. Any questions? So at least I have two spaces. One is a complex manifold. Over here, it's just a finite set. And you can also look at the algebraic closure of FQ, which you should just think of as the union of all of the, it has all of the, it's the thing at the top of the tower. FQ, FQ squared, FQ cubed. And that's where all the roots lie of any degree, of any polynomial of any degree. So again, our goal, just to remind you where we are, our goal is that we solve some kind of stability phenomenon here in these point counts. And I want to show that's on this side. We saw stability over here, some kind of stability. An example, and I want to show it over here and give the connection. OK, great. So you have an algebraic variety. Wow, now is the time to hit you with something that will hopefully blow your mind. Yeah, completely blow your mind. Yeah. I'm going to just tell you what the bridge is. The bridge between these two totally different worlds. And it's much sort of deeper than I'm saying, but OK. So let me just go generally. When X is an algebraic variety, any algebraic variety, say defined over Z, it's just for simplicity. Suppose you want to count the number of FQ points. So for example, your variety could be x to the n plus y to the n equals z to the n, right? Like from a Fermat curve. So X is that algebraic variety. If you look at, there's the Frobenius automorphism going from, well, FQ bar to FQ bar. It just takes X, goes to X to the Q, the Frobenius map, sorry. And this induces a map of the FQ points of the algebraic variety, FQ bar points. When you write out, as Ravi was saying yesterday, an algebraic variety in general, it's just locally cut out by these affine coordinates. So I might have coordinates z1 to z, I don't know, let's take an n-dimensional variety. And each one of them, I just power them up, the qth power of each. That's how you act. Okay. And the fundamental observation, which at least was made explicit, definitely at least by André Weil, the easy observation, but I think maybe Hasse probably, it's more like a viewpoint. It's not a hard observation. So you have Frobenius. So you have, the picture in your head is that you have some algebraic variety, and you have a self-map. Think homeomorphism of a surface. I know this is crazy, because it's like, this set here is some crazy set. The FQ bar points is I don't know what FQ bar, I mean, it's some totally disconnected, there's some topology, right? But the fundamental observation is that if you look at the fixed points of Frobenius, in topology we like fixed points. That's exactly the FQ points. Why? Fermat's little theorem x to the q is congruent to x mod q. So what this means is that if you look at Frobenius, it's really happening all the way up here, FQ bar. I say, look, if I'm lying in FQ, so here's FQ bar. You have FQ, FQ squared, FQ cubed, dot, dot, dot. And it's all, this is what FQ bar looks like, this tower. And you have Frobenius is acting on this whole thing. And I say, look, I'm going to take my elements 1, 2, up to, or 0, 1, 2, up to q minus 1. They're all lying in FQ, right? Each of these elements to the qth power is equal to itself. It's a fixed point of Frobenius, right? Great, so that gives a containment here. The right side is contained in the left side. The FQ points are all fixed by Frobenius. But the equation x to the q minus x, as we know, as we learn in algebra, has only q solutions, even in the algebraic closure. But you've already found them all. So you have equality. And therefore, what Andre, this is, wait for it. If somebody doesn't like run out screaming that their mind is blown and they can't, then I will have failed. So I shouldn't build it up because, but sorry, I've done this a bunch of times to people and it happens every time, essentially. So you're like, okay, I'm trying to compute like the number of FQ points. So it's like, well, ready? If I want to compute the number of FQ points of an algebraic variety, that's just the number of fixed points of Frobenius. Right? And so I know how to do a number of fixed points. So Andre Weil noticed in the very few examples, and he proved it for curves, which is deep, gee, whenever you're counting number of FQ points, it always seems to be like an alternating sum. Where have I seen alternating sums? Oh, well, look, we have a map of a space. Frobenius is acting on FQ bar. And the Lefschetz number, Lefschetz fixed point theorem, under nice circumstances, computes the number of fixed points, right? The Lefschetz number is the number of fixed points for nice maps. And so this should just be the alternating sum, minus 1 to the I, from I equals 0. Well, x is a complex variety, so it should be to twice the dimension of x, because it has, the real dimension is 2 times the complex dimension of the trace of Frobenius, going from the ith homology. Let me write cohomology. You can use Lefschetz for cohomology of, I'll write it sort of x, thinking of the FQ bar points. I won't write coefficients on purpose, to itself. So Frobenius acts on the variety, acts on the FQ bar points, so it acts on the cohomology groups. And so this is the Lefschetz fixed point theorem. Right? The only problem is that this is nonsense, because you can't apply the Lefschetz fixed point theorem to like a totally disconnected set. However, it's a long story, but what Andre Weil noticed is that this zeta function that people build, this rationality of the zeta function, for any variety, at least smooth and projective, or any variety, would follow this famous thing, this pattern in the number of FQ to the R points. Because when you put the fixed points of Frobenius to the dth power, by the same argument I gave, it's the Q to the D points. And he's like, it would formally follow. It's very easy to show. It formally follows if you have the Lefschetz fixed point theorem. The only problem is it's a meaningless, this has no meaning. So this is one of those times where you want to find a definition to make this work. That's what Grothendieck was trying to do when he designed étale cohomology. That's what étale cohomology is. But don't confuse what Grothendieck did with the current perversion. It's like ISIS perversion of Islam. The current modern perversion of Grothendieck isn't trying to do some axiomatic. He absolutely was trying to do literally count FQ points on algebraic varieties. Super duper concrete. Okay, that's what he was trying to do. Literally, it's like, if you can make this work. Now that's fundamental, and it's hundreds of pages. It's étale cohomology. But let's do a calculation. Yeah, so what do I want to do? Great. So the key thing is that this theorem works. You just put if x is smooth projective, amazing theorem. X smooth and projective, so compact. Then this works, you just put étale there. And then this is correct. And you're like, yeah, but how do I compute it? And how to compute, it's only as good as computing this thing. Right? But you can absolutely do it. And let me, in the interest of time, I'm not going to do a little general course on this stuff. But let me just say the following words, too. Oh, so, yeah, I wish I could just, yeah. he gets rationality of the zeta function. And if you know, like from classical Riemann zeta function, there's this like functional equation. That's on the side of sort of topology and analysis. There's a functional equation on this side. It's Poincare duality. It follows formally from Poincare duality. So it's this mind-blowing dictionary that algebraic topology and like the zeta, Riemann zeta function, it's like the same thing. I mean, it's been very, very powerful, and it's very, very useful. And I'm just doing like a baby case. I mean, we're just adding one little point of view here, this representation stability. Okay, so let me just give the theorem. In our case, in general, it is hard to compute. So in general, for x not necessarily, not projective, so not compact, and maybe not smooth. Everything we're going to talk about is smooth. I'm not even going to talk about varieties that have singularities, meaning like it's a manifold. In general, it's hard to compute, really hard to compute this. And when you leave the compact world, even in the compact world it is hard to compute. But when you leave the compact world, this formula is not true. And you might say, who cares? Why did all these guys, I mean, Deligne put huge amounts of time into the non-compact case. And the reason is, like, almost all the things we're faced with are not compact. Tons of things. Any kind of moduli space is not compact. The space of polynomials of degree n, where roots are not allowed to collide, that's not compact. You're not allowing the roots to collide. We can get as close as we want, right? But you're not allowed to. The moduli space of genus G Riemann surfaces is not compact. The moduli space of like smooth degree D hypersurface in Pn is not compact, because they're all described by like something not vanishing. And so not vanishing is an open condition. It's not a compact condition. So in general, I'm skipping a few. Well, let me just say this. In our case, several miracles occur. In our case, when x, I'll call it x sub n, remember this is I want to apply this whole theory to understand polynomials over fq. So on the one side we have xn of c, so forget, I'm going to call it xn, but we have poly n of c, and I want to do this bridge for poly n of fq. Oh, I started at 9 o'clock? Is that correct? Yeah. Okay, so I better end it up, but I guess what I'll do in my next lecture is to take a small variation of this formula which does hold, show you how you can compute this. One of the punchlines will be computing this essentially comes down to understanding HI, the actual like Durham cohomology. This little atoll should scare you very much. It's some totally new cohomology theory. It's very, very hard. It's hundreds of pages to construct. But here, even with like Q coefficients, this is something we've been talking about at this conference, the cohomology of the space of polynomials over C, or some algebraic or hypersurfaces over C, or rational maps over C. Just the actual honest-to-God cohomology. That's this, and you can get the trace from that. That's the dictionary. If I compute this, I get the point count. And by the way, if I get the point count, I can often get the cohomology. I'm going to like literally show you how to do it right when I start my next talk. And then you'll see, you can imagine now, like, ready, stability for this should give stability a point count, some kind of stable point count. Classical homological stability. And rep stability just makes that the trivial situation, literally, and it's much, much richer. So that's what I'm going to do in my next talks. Yeah. Thank you.